All right, next on the agenda is errors and powers for hypothesis testing. And I'll go ahead and tell you, I posted this video and wrote all this out in a previous video. At the end, I had a technical glitch. I lost the instructional video. It just completely shut down on me, and I don't feel like writing all this out again. So, hey, just play along with me, okay? Pretend that I'm writing it out and explaining it as I go. And I am going to explain it as I go. So let's say we're testing that population proportion is 40% versus it not being 40% at alpha equal 0.05. If our p-value is 0.035, what do we conclude? What's our decision? Our decision is we reject the null, right? When our p-value is less than our alpha value, then we reject. So it's tempting to draw a line through the null when we reject it and kind of conclude that our p-value, not our p-value, our population proportion is not equal to 40%. All right, is that what we can conclude? Yeah, kind of. Where we can't make a conclusion or where it's inappropriate to make a conclusion is when we start making very, very strong statements. We can't conclude with absolute certainty that the percentage is not 40%. We can't conclude with absolute certainty that this decision is correct. Why? Well, enter in the concept of errors in statistical reasoning. Now, the reason, as I've written out here, for the most part, our populations are typically very, very, very large in size, whether it's dogs, cats, elements, whatever it may be. We typically think of hundreds of thousands, maybe even tens of millions of people, right? So we are making a decision on a value from our population using a very small sample and probability. So in a nutshell, there's a chance that we made a wrong decision. I mean, it's not likely, but it's possible that our decision was based on a sample that's not representative of our population. Now, if you think back to the central limit theorem, we started out with the population, and we started taking random samples from the population, and we calculated a mean or a p-hat in this context, and we end up getting this distribution of sample means or distribution of sample proportions. It's not unreasonable to think or to conclude that we might have one sample out of all this distribution that just is not a good sample. Let me give you an example. Something just hit me. Last week was spring break at Shawnee State University, and it was actually going to be warm 2 days. So my buddy called me up, said, "Hey, let's go play golf." So on Tuesday we went to Belterra, a golf course in Indiana, played golf. It's a beautiful day. Played horribly, but whatever. So later on that night, we went into the casino, and he likes to play roulette. I don't play roulette. And we looked up on the board, and you can see that, like, I think the last 10 draws or the last 10 spins. And I thought this was interesting. There were 3 greens. Now, there's only a 2 out of 38 probability of getting a green, but there were 2 greens, 6 reds, and 1 black. Only 1 of the 10 were black, yet there's an 18 out of 38 probability of getting a black on the roulette wheel. So that 10 rows, those 10 rows were not representative of what we would get day in, day out, spinning a ball on a roulette wheel. So my point is, you know what, it happens. So because it happens, we have to define certain errors. So I think this chart does an exceptional job of displaying these errors that we encounter in hypothesis testing. There's a lot going on, so let me go through and explain each little part. First of all, the null hypothesis, the statement in H sub O, is either true or false. We don't know if it's true. We don't know if it's false. It's the reason we're conducting the test, right? But it is either true or false in some absolute knowledge universe, if you will. We make a decision. We either reject the null or we fail to reject the null. And then we have kind of 4 possible outcomes. If the null is false and we reject it, well, I put a smiley face there because that's what we want. We want to reject false statements. If the null is true and we don't reject it, then I put another smiley face because that's an outcome that we want in statistics, in hypothesis testing. We don't want to go around rejecting true statements, right? Now, the errors actually occur in the other 2 squares. So you can see in this box, I have 1 error. This represents a type 1 error. Type 1 error is rejecting a true null hypothesis. A type 2 error is failing to reject a false null hypothesis. Now down here, I've written it out. Notice type 1 error when we reject a true null. Type 2 error when we fail to reject a false null. Now you'll also notice in this box that there's a sub box here with an alpha and there's a beta. The reason I put that there is alpha that we've seen previously in all of our testing examples, hypothesis testing examples, is actually the probability of a type 1 error. Beta, on the other hand, is the probability of a type 2 error. So I write that out for you down here. Alpha is the probability of a type 1. So for example, when we set alpha equal 0.05, which we've done many times previously, we quote unquote allow ourselves a 0.05 chance of making a type 1 error. Beta is the probability of a type 2 error. I'll tell you, calculating beta is pretty sophisticated, is beyond the level of this class. Now, one more thing I want to cover is power. I'm not going to write this out, but I'm going to speak it slowly so you can write it down. Power can be calculated by taking just 1 minus beta. But again, beta is really hard to calculate. But if you had beta, you can calculate the power by just taking 1 minus beta. What I want you to know is the definition of power. Statistical power is the probability of rejecting a false null. Let me repeat that. Power in the realm of statistics is the probability of rejecting a false null. Okay? Now, if you're really involved and engaged in what I'm telling you, you probably have heard me say previously that we have a lot of choices for alpha. 0.001, 0.01, 0.05, 0.10, 0.25. Granted, 0.01, 0.05, and 0.10 are the industry standards, and by far the 0.05 is the industry standard. But if errors are bad, which by the way they are, why, and again, error is a probability of a type 1 error. Alpha is the probability of a type 1 error. If errors are bad, and if we set our alpha at 0.001, giving us a 1/1000th chance of committing a type 1 versus 0.05, which is a 5%, much higher. Or if we set it at 0.25, we have a 1/4 chance of committing a type 1 error. If errors are bad, why don't we just go overboard and set alpha at some really, 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 really small level so we don't commit any of them? Well, it's not that simple. It's not that simple because of this fact. As alpha increases, we note that beta decreases. Conversely, as beta increases, we note that alpha decreases. So what happens if we examine the 0.01, the 0.05, and the 0.10 that again are the 3 industry standards? If we set alpha low, then we're rarely going to commit a type 1 error, but it opens the door for us to create more type 2 errors. If we set alpha high at 0.10, then we're opening the door to commit more type 1s, but controlling the effect or the possibility of committing a type 2. So it may become clear to you, or I hope it becomes clear to you through this illustration, that this is the reason that 0.05 is pretty much the agreed upon level of alpha for a statistical test, because it kind of balances out the teeter-totter, if you will, of the type 1 and type 2 errors. That's it. That's all I got. I think there's one question on your homework. Well, actually, there may be more than one. I'm not sure. But just remember, in the context of type 1 and type 2, just state what a true null means, right? And the impact of rejecting it for a type 1. And then in the context of a type 2, again, let's go back to the chart. It'll make it much clearer what I'm saying. In the context of a type 2, think about what a false null is and what the context would be of failing to reject that. All right, that's all I got. Take care.